I can only answer your question with the nuclear transportation on an in vitro and tissue-related aspect, not in vivo. So we did, since more than 10 years, we did a lot of studies with in vitro cell cultures, with three-dimensional cell cultures, and with tissues, and with human tissues as well. And we investigated not only titanium dioxide, but also many other materials. And we have a very, very good TEM support in our own lab. And we never, I repeat it, we never saw such material inside of the nucleus in thousands, in more than 10,000 of slices. And you have heard Paul Bohm yesterday, he made the same studies before, and he never saw in the nucleus as well this material. So you are totally right, there are some artifacts. I showed some of the other artifacts yesterday. It's precipitation of contrast materials, it's drag and drop via the slices to make it. Another study, not from us, from Bern, I mentioned yesterday with the tomograph. So you can avoid the drag and drop phenomena in slicing thicker slices, 200 and 250 and 500 nanometers thick. They slice it, and they have a tomograph, a TEM tomograph, and can make three-dimensional pictures of it. So their drag and drop is not possible, and they don't find particles in the nucleus. So I exclude it.
But I think it's the usual problem, as we discussed earlier, is you have one or two or three positive demonstrations, and can all of the robust negative demonstrations remove that concern? To my mind, if I wanted to answer that question and I was designing an experiment from scratch, I would treat some cells, I would then gently lyse those cells to isolate the nuclei, purify the nuclei, and look for titanium in those isolated nuclei. We can do that for a comet assay, we can isolate nuclei for a comet assay. Why can't we do it to answer the question, does titanium actually get inside the nucleus?
So Dr. Crook said you can do it, but
you will not find it. And another thing is, look carefully in these publications that have shown particles inside of the nucleus. They never made an EDX elemental positive control. They always only support the idea they find a black dot and they say, this is my material. But they never showed EDX. We showed EDX in slices, and we showed it in the cytoplasm and lysosomes, and we never found it in the nucleus. So why don't they do EDX? You can do it. You have not to isolate the nucleus.
Professor Lansdowne.
We know from Kirk-Othmer that the molecular identity of titanium dioxide is robust and strong. Are you going to suggest that the microfine particles have different physical-chemical properties which could facilitate the entry into the nucleus and maybe facilitate some form of DNA adduct formation?
I'm not suggesting that, and I think from what Professor Krug just said, I don't think any of us are suggesting that even with microfine, nanoparticle-sized TiO2, that there is a potential to actively enter the nucleus. Okay, so one can always raise concerns, well, what if there is tissue damage? What if there is cellular damage? What happens during cell replication when the nuclear membrane is dissolved? What happens then? But you know, all of these studies, nearly all of these studies looked for other genotox endpoints at the same time. And as Maria mentioned, some of those studies show DNA strand breakage. They show reactive oxygen species. Nearly all of them show some form of oxidative stress, but not all of them show there's a genotoxic finding. So there is a real mishmash of data. None of it is robustly consistent with the ability of any of those particles to enter the nucleus.
Dr. Donner, maybe on the same point?
Yes, I don't really have anything to add to what David said, but I do agree that there is a complete mishmash. And I think part of the problem is that often when you do test, for example, titanium dioxide, you don't really know what you are testing after all. You don't know the exact form and the shape. I do believe that the smaller the molecule, of course, you're going to have a different behavior with the cell than if you have a very large molecule that might not even enter the cell. But I do think that this might be something that you had to pay more attention to when you do work, and it's not always that easy because we are very rough. We have these sophisticated characterizations up front these days, and what happens next? We try to dump it in water and shake it and pour it on cells in tissue culture. So there are lots of things happening. So in a way, we have characterized what we are going to test, but we don't really know what we are actually testing once it hits the in vitro cell system. So it's equally complicated in a way. I mean, we have gone down from human to rodent to cell now, and in vitro testing has its limitations, which is really, really hard, but they have to be recognized also when the evaluation of the data.
Professor Oberst.
Coming back to the nuclear entry, and I agree completely with what you were saying, David, and Harald, what you were saying, but couldn't there be an argument, well, there may be, during the cell division, there may be some interaction with the material, and then you get it inside?
There may be, and if that occurred, I think what you would expect to see would be aneuploidy, because you would see disruption of spindle function, most likely. And I don't think any of the in vitro micronucleus studies probed the micronuclei for presence of centromeres, or did they?
No, I did not notice that they would have.
So I don't think we know whether that... So, but if it was that, it would have a threshold. So does it really matter?
Dr. Krug?
Another point regarding this. Of course, we did our exposure situations in the in vitro cells cultures for 48 hours, for 72 hours. So we have a minimum 1 or 2 cell divisions during this time. And of course, the argument is the degradation of the nuclear membrane, the envelope, and after division it fixes again, and then just by chance you have the material inside of the nucleus. No, it is not the case. The cells exclude all the foreign materials, as they exclude Golgi apparatus, vesicles, and other material. They exclude everything that is not belonging into the nucleus, and they exclude the nanoparticles as well. We had never have seen, after several cell divisions, and we treated cells during half a year of passages continuously with nanomaterials, we never found the material in the nucleus.
Okay, Professor Oberst.
Again, trying to play the devil's advocate. So how, in vitro, that's fine, what you were saying. How about in vivo? You have a prolonged exposure and then you don't know anything what happened before.
But if that was going to happen, then we are looking at a chance event. It would be the chance that the reforming nuclear envelope of a divided cell happened to include a nanoparticle. In all honesty, could that realistically, that chance event, could that realistically describe a genotoxic risk? We're not actually seeing any positive results in vivo. So we are below, even if it's happening, we are below the threshold of induction of any genotoxic effects. And one starts to think of applying things like the threshold of toxicological concern. If it's happening, it is so minimal, it is so negligible, it has no biological consequences.
I tend to agree, right? Yeah.
On the same point? Totally different point. Okay, let's finish this one, see whether we have any more interventions on after the agreement on the part of Professor Oberst. That seems to conclude that part of the conversation. Jan Prochaska, 15.
I have a question to your previous talk. Did I understand correctly that ECHA actually works in a sort of chamber political mode, and the decisions are not made on a broad consensus of experts? That's what you said there?
Yes, I mean, you have to forgive me. I have never attended one of the ECHA review committees, regulatory assessment committees, and so on. So this is feedback that I've received from companies who have attended those. My impression is that there are panels put together. Len, you may know more. No, go on. I'm trying to draw you into this.
Yeah, microphone. We don't want to miss a single word of what you say, Professor.
There will be panels of experts. The member states will nominate experts, but we don't necessarily know who they are, and we don't know. I don't think I know how they reach their final conclusions. Whether it is driven by a small number of people who can speak very loudly, or whether there is a vote, or how they reach consensus, I am not entirely sure.
Professor Levy?
I think Professor Grime would be the person to give you some insight on how such systems might operate.
Helmut,
hey, what a good idea. Professor Grime. I'm sure at the end of this conference, just between us, you can tell us a few things that we don't know yet about how proceedings go there.
That it's not polite to ask me how they come to a conclusion. No, the situation is usually there are 1 or 2 or 3 rapporteurs, and they prepare the document, and the comments on the on whatever is submitted as other comments from outside, and they prepare this document, and they actually go back to their experts at home, preparing these responses. And then more or less people accept the opinion of the core group, unless it's disputed. And in many cases, it is actually disputed. So there is the possibility that there is a general discussion on a certain thing. But when it goes into details, as it is in other committees, it's always driven then by some people who are considered to be the experts.
Okay, thank you very much for that insight. We're a little over time for this session, so I'll just have to ask you for maybe one final thought to conclude this before we move to the final session. Final thought?
I was going to make one comment on what Maria was saying about the fact that the test guidelines do not really give us any help, any guidance on how to test nanomaterials. There are some exercises that are going on. There's an exercise within Europe which is looking at the best ways to test for nanoparticle genotoxicity. I think the Ames test will be excluded. I don't think that's going to be appropriate. I think the in vitro micronucleus test is likely to be one of the favored options, but you have to be very meticulous that you separate the treatment with the nanoparticle from the treatment with cytokeratin B, which is used to generate the binucleate cells that we actually score. So there are some rigors that would have to be applied. But that is still an ongoing process. So at the moment, we have the tail wagging the dog. We have the political wish and the regulatory desire to test nanoparticles for genotoxicity, but the science isn't actually ready. So it will take some time.
Dr. Donner, you will have the final word in this session.
I may like to add that since we're focusing on TiO2, it may sound like this would be the only problematic things we have to test, but unfortunately it's not. We have problems with almost everything we test. We have problems with fibers, we have problems with aerosols, we have problems with TiO2, frankly, was mostly that people came and said, this is a paint, what do you want me to do? And go from there. But the same principles apply. The test guidelines are applicable to a certain point, but at a certain point they leave you completely alone. And this is where you feel that you're submitting your dossier into a black box. because you don't really know how the reviewers are going to look at it, and there seems to be an emphasis always on the positive result. It might be an old mouse lymphoma asset as 30 years old or something, and there is a little indication, and you find yourself in a suite of additional testing. And I just hope that this is not going to happen for nanomaterials as well, that whatever you submit, it's not going to be considered the final word or adequate enough. Thank you.
Okay, thanks to both of you.